time. Okay, so in the previous 2 lectures, we saw on we learned about drawing the Lewis structure of a molecule. And what we learned, when you want to draw for some reason, my call dropped, so let me go back. I'm sorry for this mess up. These atoms, when they are involved in chemical bonding, they want to have a complete shell of outer electrons. They will want to have 8 electrons in their valence shell. So that's why We're following the octet rule. But there are elements that are involved in chemical bonding that will not have 8 electrons around them. So as a result, there are molecules that have incomplete octet. And this is the case when you have hydrogen. For example, if you were to draw the Lewis structure for the hydrogen molecule, H2, you have a hydrogen that has got 1 electron in its valence shell, and then this hydrogen has formed a covalent bond with another hydrogen that has got also 1 valence electron. So there is no way 1 plus 1, 2 can make 8. Even if we want to have 8 electrons around the hydrogen, it's not possible. That's why hydrogen is a notable exception to the octet rule. But hydrogen molecule is a stable molecule because it does not necessarily have to have 8 electrons, because all hydrogen wants is to have the electron configuration of its corresponding noble gas, helium, which has got 2 electrons. So hydrogen, even though it does not follow the octet rule, even though hydrogen does not have a complete octet of electron, it is a stable molecule. It is a valid Lewis structure because it will have 2 electrons when it forms a bond with other element, just like that of the corresponding noble gas helium. The other element, they follow the octet rule because they want to have the electron configuration of their corresponding noble gases, that of neon, argon, krypton, xenon, etc., which have 8 electrons in their valence shell. But there are still other elements in the periodic table. When they form a bond with other element, they will not have 8 electrons. Some of these happen because there are not enough electrons in such atoms to provide octet of electrons around the central atom. Examples of such are chemical compounds that are formed by beryllium, which is a group 2A element, and boron, which is a group 3A element. For example, let me just give you an example of beryllium, okay? Beryllium forms a chemical bond with hydrogen. This chemical compound is called BeH2, okay? Beryllium forming 2 bonds with hydrogen. This is a stable compound, a known compound. Then when you look at this molecule BeH2, this molecule has got 2 hydrogens and 1 beryllium. When you draw the Lewis structure, the first thing we were told is to arrange the atoms the way you think they are bonded to each other. So we'll put beryllium in the middle, and then on the sides we will have the 2 hydrogens, the hydrogens being on the outside. The second rule we're told, the second step we're told to follow is count the valence electrons. So hydrogen has got 2 valence electrons, the 2 hydrogens, each of them having 1 valence electron. So from the 2 hydrogens, we'll get 2 electrons. And then beryllium being a group 2 element, it will have 2 valence electrons. So can you tell me what the total valence electrons in BeH2 is? What is the total valence electrons in BeH2? Hello? What is the total number of valence electron in BeH2? How many are there? Huh? Hello? This Peter is disturbing for no good reason. I asked a question, I thought that's what you are unmuting. See, we have this molecule of BeH2, where you have a beryllium that has formed chemical bond with hydrogen, with two hydrogens. The valence electron, the number of valence electron for hydrogen is 1. So we have two hydrogens. The total number of valence electron that come as a result of the hydrogen is 2. Beryllium is a group 2 element. Since it's a group 2 element, the number of valence electron on beryllium are 2. 2 valence electrons coming from contributed by the hydrogen, and then 2 valence electrons contributed by beryllium. Therefore, the total number of valence electrons of BeH2 are 4. Okay? So there is no way you can have 8 electrons coming out of 4. Even if we want to have 8 electrons around the beryllium, we do not have enough electrons to allow that. As a result, the Lewis structure for beryllium will be BeH2, and around the beryllium we have 4 electrons. And this is a valid Lewis structure for BeH2. We do not have enough electrons to provide the 8 electrons beryllium would want if it wants to be stable like that of carbon, nitrogen, oxygen, and the halogens. We do not have the electrons that are required to put 8 electrons around the beryllium. We only have 4 electrons. So the maximum number of electrons that can be around the beryllium are therefore 4 electrons. So this is a valid Lewis structure for BeH2. It has incomplete octet of electrons. So group 2 elements, when they form a covalent bond, if you look at the central atom, it can only have 4 electrons around it. The other group of elements that will have incomplete shell of electrons are the group 3 compounds that are formed by group 3A elements, like that of boron and aluminum. So when boron forms a chemical bond with other elements, it can only form 3 bonds. The same to aluminum, it forms 3 bonds. So if you look at these molecules around the boron or the aluminum, we can only have 6 electrons around them. 6 electrons around the boron, 6 electrons around the aluminum. So these molecules will have an incomplete octet of electrons. Even if we want, there is no way we can have 8 electrons around the beryllium, 8 electrons around the boron, and 8 electrons around the chlorine. So these molecules, the central atom in these molecules will have an incomplete shell of electrons. They will have an incomplete octet. And there is nothing we can do about it because we do not have enough electrons to give them octet of electrons. As a result, these are the valid Lewis structures for these molecules. So if you look at compounds of boron and compounds of aluminum, they only have 6 electrons on the boron and the aluminum. These elements, they will want to have octet of electrons like the other elements in their neighborhood, like that of carbon, like that of oxygen, like that of fluorine, chlorine, etc. As a result of that, such type of molecules are very highly reactive. They react, therefore, so that they can accept additional pair of electrons. So when they accept additional pair of electrons, they will have 8 electrons like that of carbon, nitrogen, oxygen, fluorine. As a result, these compounds are very, very highly reactive. They are not stable. So in this particular case, there is nothing we can do about this because there simply are not enough electrons to form an octet. They will have an incomplete octet. So because beryllium and boron atoms have less than an octet of electrons, these molecules are very highly reactive. So aluminum trichloride, for example, which is a compound in which the aluminum, the element below boron in group 3, has an incomplete valence shell. And so since it has got an incomplete valence shell, since its shell is only partially filled, it will undergo a chemical reaction with other elements that have electrons to donate to it. As a result, it is very, very highly reactive. So the first type of exception to the octet rule is elements that have incomplete octet of electrons. They will have incomplete octet of electrons because there are not enough electrons to be distributed among the elements involved in chemical bonding to have octet of electron. For example, as I told you, in the case of BeH2, beryllium has 2 electrons in its valence shell, and then the 2 electrons contribute 2 electrons. 2 plus 2 is 4. The total number of valence electrons in BeH2 are just 4 electrons. So you cannot generate 8 out of 4. Even if we want to give the beryllium 8 electrons, we do not have enough electrons to provide 8 electrons to the beryllium. So at the end of the day, you will have the beryllium in this molecule having only 4 electrons around the beryllium. The same to boron and aluminum. They can only have 6 electrons around the central atom. As a result, these molecules have incomplete octet of electrons. Even if we want to give them octet of electrons, we do not have enough electrons to achieve that. Since these compounds, since the central atom in these compounds does not have octet of electrons, and as a result are not stable, they undergo chemical reactions. They are very highly reactive. By reacting with other elements, they will have a reaction in which electrons are pumped to the boron or to the aluminum so that they can have octet of electrons. So as a result, they are very highly reactive. So this is the first exception to the octet rule. Then the other exception to the octet rule is those elements that have expanded octets. Those elements that have more than 8 electrons in around their atoms when they form a chemical bond. So such type of molecules are said to have an expanded octet. So let me explain to you why. Yes.
Yes,
Hello?
Amos. Yes.
Yes.
Where you have written boron and aluminium exhibit high reactivity. What about beryllium?
Even beryllium compounds are very highly reactive, okay?
Yes.
Because the reason why they are reactive is because they don't have octet of electrons, okay?
Yes.
Yeah. And then we cannot give them octet of electrons because we do not have enough electrons. Even if we want to, we do not have octet of electrons, okay? 8 electrons to give them, okay?
Yep.
Yes. Okay. So the other exception is the expanded octet, meaning there are some elements when they form a chemical bond around with other elements, when you count the number of electrons around those elements, you'll find that they have more than 8 electrons. So another exception to the octet rule occurs with some element located in the third row of the periodic table and later in the periodic table. In these elements, you will see after they are formed a chemical bond, a covalent bond with other elements, you will see that they have more than octet of electrons. So we'll try to understand why these elements have more than octet of electrons. Let's first discuss this. For example, if you take carbon, nitrogen, oxygen, and fluorine, this element in the second period of the periodic table, they follow the octet rule because the number of electrons that is required to fill the valence shell of the second shell is 8. 2 of them being in an s orbital, in the s subshell, and 6 of them being in the p subshell. To fill the s subshell, you need 2 electrons. To fill the p subshell, you need 6 electrons. 2 plus 6, 8. So to have a complete shell in the second shell of the periodic table, you only need 8 electrons. Okay, that's why they follow the octet rule. They react so that they have a completely filled outer shell, 8. But when you go to elements in the third row and later in the periodic table, these elements, in addition to S and P subshell, they also have the D subshell. So to completely fill the third shell, in addition to fill the S and P, which take 2 plus 6, 8 electron, you need additional electrons to fill, to completely fill the third shell. As a result, when elements from the third row of the periodic table, when they form compound with other elements, they can have more than 8 electrons around them after they are formed a particular chemical bond. Because in these elements, like sulfur, for example, like phosphorus, because sulfur, if you look at oxygen is in the second period of the periodic table. Then sulfur is in the third shell. So below oxygen, you have sulfur, which is in the third period of the periodic table. In oxygen, in its valence shell, we only have 2 types of subshells, the S subshell and the P subshell. But in sulfur, in the valence shell, in addition to S and P, we have d orbitals. And these d orbitals are empty. And therefore, in order to become stable, these d orbitals need also to be filled. So after filling the S and P orbitals, which carry a maximum together of 8 electrons, some of the electrons will go to fill the empty d orbitals. As a result, in an element like sulfur, you can have more than 8 electrons once it has formed a particular compound. The same is true for phosphorus. If you look at phosphorus, phosphorus in the periodic table is below nitrogen. nitrogen, and then below it you have phosphorus. Phosphorus, just like sulfur, in addition to the S and P subshells, it has the D subshell in its valence shell. As a result, in addition to filling the S and P, some of the D orbitals, some of the empty D orbitals will also be filled. As a result, when sulfur and phosphorus form compounds with other elements, when they form covalent bonds with other elements, they can have more than octet of electrons. So let me just give you examples. For example, what we are going to see is the compounds of sulfur and phosphorus, okay? The simplest compound of sulfur, which we are going to look at first, is hydrogen sulfide. In hydrogen sulfide, which is HS2, around the sulfur, you will see 2 lone pair of electrons on the sulfur. Those are 4 electrons. And then the same sulfur has formed 2 covalent bonds with 2 hydrogens. So when you count the total electrons surrounding the sulfur, you will see there are 8. So you will have 8 electrons around the sulfur, following and obeying the octet rule. But if you look at the sulfur in this particular compound called dimethyl sulfoxide, you will see around the sulfur, how many electrons do you see around the sulfur in dimethyl sulfoxide? How many electrons do you see on the sulfur or surrounding the sulfur?
10.
10, because you have these 2 lone pair of electrons, 2, and then 4 electrons as a result of the double bond, additional 4 electrons as a result of the 2 single bond between the sulfur and the carbon. So 10 electrons around the sulfur. This is a valid Lewis structure for dimethyl sulfoxide, where the sulfur has more than 8 electrons. It has an expanded octet of electrons. Then when you look at sulfuric acid, an acid which you have studied and learned about all the way from primary school, sulfuric acid, you will see around the sulfur, how many electrons are there on the sulfur?
10.
A low count, very well. In sulfuric acid, how many lines do you see around the sulfur?
12.
You see 6 lines. 6 lines around the sulfur. Then each of the lines are because of overlap of 2 electrons. Okay, so we have 2 double bonds. As a result, those 2 double bonds bring 8 electrons, and then we have 2 single bonds. So 8 plus 4 in total, we have 12 electrons around the sulfur. So on sulfuric acid, the sulfur has an expanded octet of electrons. How about in phosphoric acid? How about the phosphorus? How many electrons do we have on phosphorus?
10.
10 electrons, okay?
10.
So we can have expanded octet. We can have more than 8 electrons when elements in group 3 of the periodic table and further in group 4, in group 5, when element in period 3, period 4, period 5, period 6, period 7, etc. of the periodic table, when they form chemical bond with other element, it is possible that this element can have more than 8 electrons. They can have 8 electrons, as in the case of hydrogen sulfide. They can also have 10 electrons, as in the case of dimethyl sulfoxide. They can have 12 electrons, as in the case of the sulfur in sulfuric acid, or like phosphorus can have 10 electrons, as in the case of phosphoric acid. So what we have learned, please mute. What we have learned, when drawing the Lewis structure, one, we only involve the valence electrons because they are the ones that are involved in chemical bonding. So we count the valence electrons of the element that are involved in that particular chemical compound. And then we follow the octet rule, we follow the duet rule. The reason why, for example, we follow the duet rule for hydrogen is because hydrogen is in period 1 of the periodic table. In the first period, to completely fill the first period of the periodic table, you only need 2 electrons. That's why hydrogen follows the duet rule. Then we also follow the octet rule. We follow the elements like carbon, nitrogen, oxygen, fluorine, follow the octet rule because these elements are in the second period of the periodic table. To completely fill the second period of the periodic table, you need 8 electrons. So this element will be involved in chemical bonding in order to have octet of electrons. But if you have elements further than group 2, element in group 3, 4, etc., in these periods of the periodic table, in addition to the S and P subshell, we also have the D subshell, which has to be filled. For example, if you look at the third shell of the periodic table, the maximum number of electrons that are allowed in the third shell of the periodic table are 18 electrons, not just 8. So it is possible, of course, it cannot be, you will not have a situation where a particular element can have 18 electrons around it. That is impossible. But you can have those elements like sulfur and phosphorus, which are the most common elements that are involved in chemical bonding with carbon. In this element, you can have 8 electrons. You can also have more than 8 electrons. So we can have an expanded octet as an exception. The other exception is the incomplete octet of electron. Those elements, when they form a chemical bond, a stable chemical bond with a valid Lewis structure, in these molecules, there is no way we can have octet of electrons. The reason being, there will not be enough electrons, even if we want to give these elements octet of electron. The simplest and clear example of this is BeH2, where you have 2 valence electrons on beryllium, because beryllium is in group 2 of the periodic table, and then the 2 hydrogens, since they belong to group 1, they bring 1 valence electron each. So the total number of valence electrons in BeH2 are 4. Even if we want to, there is no way we can have more than 4 electrons around the beryllium. So this element will have incomplete octet of electrons. Is it okay? Hello?
Yes,
Okay. Now,
it's okay.
now let's go to another concept, okay? Let's discuss about resonance, okay? I'll first define what resonance is, and then I will explain using an example why for some compounds it's not possible to represent their structure, the structure of their compound, such compounds by a single structure. So let me first define what resonance is, okay? So resonance is the property of having a structure, a molecular structure, which cannot adequately be represented by a single structure, but is a composite of 2 or more structures, and then these 2 or more structures have high energy. This is what is known as resonance. So resonance comes as a result of failure to represent the structure of a compound by a single structure. So let me just give you an example. Okay, I will unshare this one, then I will write on my notepad and see. Okay, so let me unshare this and open a blank slides so that I can have a discussion with you. Where did it go? Just give me 1 minute. Okay. Can you see a blank slide? Hello?
Yes.
Yes.
Okay. So please mute your mic. Mute your mic, and you'll only unmute when you want to have a discussion or talk with me. Okay. So what I want us to do is draw the Lewis structure of this molecule. Okay. Let us draw the Lewis structure for the acetate. It's called acetate, okay? The acetate ion. We want to draw the Lewis structure for CH3 CO2 minus, okay? So you remember the first step when drawing the Lewis structure is arrange the atoms, okay? We arrange the atoms. When we arrange the atoms, of course, we'll put the hydrogens on the outside, etc. Okay. So in this particular case, the way you are given, you have a carbon that is bonded to 3 hydrogens. Then you have another carbon that is bonded or connected to 2 oxygens. So the arrangement will be carbon. You have hydrogen, 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 then carbon, which is bonded to 2 oxygens. This is how the atoms are arranged. Okay, so let me copy this one. Okay, so the first step is to arrange the atoms. This is how we arrange them. And then the next step is count. Count the valence electrons. Okay, now in this molecule, we have 3 hydrogens. Sorry, 3. In this molecule, we have 3 hydrogen, 2 carbons, and 2 oxygens, okay? Now the valence electron for hydrogen is 1, so 3 times 1. And the total number of electrons as the result of the hydrogen are 3 electrons, 3 valence electrons. Carbon, we have 2 of them. The valence electron for carbon, yes.
I'm not seeing the screen.
You are not seeing the screen. Okay, let me unshare and reshare, okay? I hope you can see it.
Yes.
You can see it now.
Yes.
Miracle. Okay. 2 times 4 electrons for the carbon, 8. Then oxygen, we have 2 of them, 2 times 6. 2 times 6, 12, isn't it? The total number of electrons as a result of this are 3 plus 8, 11, 11 plus 12, 23, isn't it? But we are drawing the Lewis structure for CH3, CO2 minus. It has got a -1 charge. Since it is -1, because it has gained 1 electron. So the total number of electrons will be this one plus 1 electron. So the total number of valence electrons of the CH3 CO2 minus are 24 electrons. Okay, let me start. Okay, we want to draw the Lewis structure for the acetate ion, which is CH3 CO2 minus. To draw the Lewis structure, this is an ion, be it an ion or a neutral molecule, whatever the case, when you are drawing, the Lewis structure will be following the same rules and the same steps. Then when you look at carbon and oxygen, these are elements in period 2 of the periodic table. Therefore, they must follow the octet rule. Then hydrogen is in group 1. Please mute. Hydrogen is in group 1 of the periodic table. Hydrogen must follow the Dwight rule. That we know. So when you are writing the Lewis structure, the first step is to arrange the atoms. So when you are arranging the atoms, we put the hydrogens on the outside. Okay? And then carbon, we surround it by 4 atoms. And then we have the 2 oxygens on this carbon. So this is how the atoms are arranged. After we have determined the arrangement of the atoms, I don't know who is, seriously, who is Julius? You're the one who is disturbing now, not Julius. There's another one. Even Julius, why are you unmuting? Don't unmute, okay? Just bring Julius. Julius, why are you unmuting? So the second step is count the valence electrons. So in the acid ion, we have 3 hydrogens, 2 carbons, and 2 oxygens. When you count and add the total valence electron, you'll find there are 23. But the acid ion has a -1 charge. So if it is negatively charged, if it is -1 charge, you have to add 1. So the total number of electrons is 24. Okay? So this is the arrangement of the atoms. So in the third step is you have these 24 electrons. You use these 24 electrons to form bonding electrons, to use these ones to form chemical bond with this element. So we have to form a chemical bond here, a chemical bond here, a chemical bond in here, like that, like that, like that. When we do that, we will have used 1, 2, 3, 4, 5, 6. We formed 6 covalent bonds. As a result, we have used 12 electrons. Only 12 electrons are used. So the balance of electrons is is 24, which is the total number of valence electrons, minus the 12 we have used in forming the single bond. 24 minus 12, 12 electrons, okay? We have 12 electrons that are left. And then we'll use these 12 electrons to fulfill the octet of the element whose octet is not fulfilled. If you look at the carbon, this carbon has got only 6 electrons around it as a result of the 3 sigma bonds. So this carbon does not have octet, no octet. Then if you look at both oxygens, this one as well as this one, they have only formed a single bond. Then as a result of that single bond, they only have 2 electrons. All the same, they do not have octet, no octet. Okay, now you'll use the remaining electrons as lone pair of electrons to fulfill the octet of the element who do not have octet of electrons. So now what we have is, we have a carbon that is bonded to 3 hydrogens like this, and bonded to another carbon, and then this carbon is bonded to 2 oxygens. Neither the 2 oxygens or the carbon that's attached to this oxygen has octet of electrons, but we have this additional 12 electrons. Now we will use these additional 12 electrons to fulfill the octets of the oxygens and the carbon. So when you do that, the first set of element whose octet we must fulfill are the elements that are on the outside. See, carbon is at the center. The elements that are on the outside whose octet of electrons is not fulfilled are the 2 oxygens. So we first fulfill the octet of these 2 oxygens using the lone pair of electrons. So the number of lone pair of electrons, the number of electrons that is left after forming the single bond are 12 electrons. Now we'll use these 12 electrons to fulfill the octet of the 2 oxygens as much as possible first. Now, if you look at each of the oxygens, they have formed a single bond with a carbon. As a result of that single bond, on each of the oxygen we have 2 electrons. How many additional electrons will these oxygens need to have octet of electrons? Can you tell me how many additional electrons this oxygen will need to have octet of electrons?
4.
No.
4.
Why are you saying 4? Why are you saying 4?
6.
Huh? How many?
6.
Because each of them have 2. To have octet, to have 8, they need additional 6 electrons. So what you do, these 12 electrons, you start giving them to the oxygens, okay? So let me put, please mute. 1, 2, 3, 4, 5, 6. I've used, of the 12 electrons, 6 of them to fulfill the octet of one of the oxygen. I'm still left with additional 6 electrons. I will use those 1, 2, 3, 4, 5, 6 electrons. Okay. So what we have done, please mute your mic, please. Because if you don't mute when I send you this recording, it will just be full of noise, which is not going to be helpful. Okay. So now, if you look at this structure, we have used all the 24 electrons. We use 6 of them in forming chemical bond between the elements that are involved in chemical bonding in this particular molecule, as shared electrons. 6 shared pair of electrons. Those are 12 electrons. Then 12 of the electrons, we use them as lone pair of electrons. So all 24 electrons are used. All 24 electrons are used as bonding and non-bonding electrons. Then when you look at this oxygen, it has got octet. When you look at this oxygen, it also has octet. When you look at this carbon, it has got octet. And all the 3 hydrogens have duet, but this carbon at the center, it does not have octet. Okay? So let me draw it again, okay? Please mute. Let's mute. So we have the carbon that are formed covalent bond with 3 hydrogens. This is very clear. Then we have this carbon that has formed covalent bond with 2 oxygens. And then both oxygens have 3 lone pair of electrons. But this carbon does not have octets. So how can we fulfill the octet of this carbon? How can you have octet of electrons on that carbon?
Use a double bond.
Form a double bond, isn't it?
Yes.
So how many oxygens do we have?
2.
So let me call one of them A, okay? Let me call one of them A. Oxygen A. The other one, oxygen B. So now, you said we use the lone pair of electrons and form a double bond, isn't it?
Yes.
I can use the lone pair of electrons of oxygen A to form a double bond, isn't it?
Yes.
I can also use the lone pair of electrons of oxygen B to form a double bond with a carbon, isn't it?
Yes.
Yes.
How many possibilities do we have?
2.
2.
Two possibilities. We can use the electrons on either oxygen to form a double bond with a carbon, okay?
Yes.
So is this, for example, if one of your classmates, sorry, please mute please, to avoid all this noise. One of your classmates will use, for example, the electrons on oxygen A to form a double bond. And then your other classmate will use the electrons on oxygen A to form a double bond. As you can see, both of them are correct. There is no mistake they have done. So what is going to happen? When you draw the Lewis structure for this molecule, you can come up with 2 different structures. One where you have carbon, hydrogen, hydrogen, hydrogen. Then you have carbon. If we are using the lone pair of electrons on oxygen A, we can form a double bond here. That oxygen A will only have 2 lone pair of electrons, as it has used one of the lone pair of electrons to form a double bond with the carbon. The other oxygen will have 3 lone pair of electrons. This is one possibility. The other possibility is to use the electrons of oxygen B to form a double bond with the carbon. So this one will be a single bond. While this one will be a double bond. Okay, how many structures do we see now for the acetate ion? This structure, which I can call Roman number 1, and this other structure, which I call Roman number 2. So what has happened now? We failed to represent the structure of the acetate ion with a single structure. We followed the rules of drawing the Lewis structure of molecules step by step without any mistake. But we end up having 2 possible structures for the acetate ion. The structure of the acetate ion cannot be adequately represented by a single structure. We have 2 different structures, structure 1 and structure 2. So now what this is telling us, ideally, or in most cases, we can adequately represent the structure of a molecule by a single structure. For example, the way we have seen, all the examples we have seen so far. The structure of methane is represented by 1 structure. That of methanol is represented by a single structure. That of ethene is represented by a single structure. That of ethane is represented by a single structure. But now, when we try to draw the Lewis structure of the acetate ion, we failed to represent it by a single structure. Is it okay? Hello? Hello?
Yes.
Yes.
So the structure of some molecules cannot be adequately represented by a single structure. When this happens, please mute. Hello? Please mute. So when this happens, we have a new theory that explains this situation called resonance. Okay? So resonance coming, resonance structure, etc. coming when we fail to represent the structure of a molecule adequately by a single structure. When the structure of a molecule can be represented by more than 1 structure, we have the theory of resonance that comes to play. So I have not yet explained this theory, okay? But what I have just presented to you is that it is not always possible to represent the structure of some molecules, the structure of molecules all the time by a single structure. The structure of some molecules will be represented by at least 2 structures. As we shall see later, it is possible they are represented by 3, by 4, by 5, by 6 different structures. Now, let us concentrate on this, on any of them, on A or B. First of all, what we want to do, of course, for this structure to be complete, we must put the charges. You remember, the acetate ion is CH3 CO2 minus. It has got a net charge of -1. So we have to calculate the formal charges on each of the elements to determine which of these elements of the acetate ion is the one that brought this -1 charge on the acetate ion. So if you do simple calculation, you'll find that the charge on this oxygen is -1. And the charge on this other oxygen is -1. You remember, I have told you, you can do formal charge calculation, okay? And then you'll determine that the charge on the carbons is 0, the charge on this oxygen is 0, while the charge on this oxygen is -1. But you remember what I have also told you, you can determine the formal charge on a particular element without doing a calculation. Because we said when an element like carbon, like nitrogen, oxygen, etc., and sulfur, etc., when they form, the number of bonds they usually are required to form, they will become neutral. For example, oxygen is in group 6 of the periodic table. It usually forms 2 bonds. So if you see oxygen that has formed only 2 bonds, as it is required, that oxygen will be neutral. But if the oxygen forms more than 2 or less than 2, it will be charged. If it forms more than 2, it becomes positively charged. If it forms less than 2, it becomes negatively charged. So if you look at this oxygen B in structure 1, it has only formed 1 bond, a single bond with the carbon. It has formed less than 2. As a result, it has got a -1 charge, the same to the other one. Is it okay? Hello? Okay, now?
Yes.
So now let me just put it back again. Let me draw them again as I explain further. So if you look at the acetate ion, the 2 structures, okay? So we have one structure like this that has a double bond here. And a single bond on this side. Another structure please mute. Hello? Mute your mic. Yes, please ask. Hello? You can go ahead and ask your question. Hello, what is your question? Okay, I'm not hearing anything. So let me continue with my class. So we have this to structure 1. Hello?
I'm asking.
Yes.
You say that if a molecule forms more or less the bond is supposed to form, it becomes charged.
No, what I said, listen what I said. For example,
Yes.
oxygen is in group 6 of the periodic table. And to have octet of electrons, just mute please. To have octet of electrons, it will need additional 2 electrons. That's why oxygen usually forms 2 bonds, okay? As in the case of the molecule of water, H2O. So when you have an element, and when you see that element forming the number of bonds it usually forms, that element will be neutral. Like if you look at oxygen in a chemical compound, and then you see that oxygen has got 2 bonds. These bonds could be single bond, 2 single bonds. There could also be 1 double bond, okay? When that happens, that oxygen is neutral. But when you have an element, if you count the number of bonds it has formed, if you count it to be more than or less than the number of bonds which it usually forms, it becomes charged. It becomes ionic, positive or negative. I have discussed this in the previous lecture. So when an element forms less than the number of bonds it usually forms, it becomes negatively charged. When it forms more than the number of bonds it usually forms, it becomes positively charged. The simplest example we can use is water. I mean oxygen. H2O, when you have oxygen forming two bonds with the two hydrogens, that oxygen is neutral. But if you have the hydroxide ion, HO, from sodium hydroxide or from potassium hydroxide, the oxygen is negatively charged because the oxygen has formed less than 2. The other example is H3O, hydronium ion. In the hydronium ion, you see the oxygen has formed 3 bonds with hydrogen, and that oxygen is positively charged. Okay? So that's what I have discussed. Now, coming back. Hello? Yes?
Yes, I understood those parts that you just stated. So my question was, why does this not apply to ozone?
We'll talk about ozone, okay? And in ozone, there are positively charged oxygen, negatively charged oxygen, neutral oxygens, okay? In ozone. So we'll discuss about the structure of ozone. In fact, the structure of ozone is one of your assignment, okay? But I will teach you the concept of resonance very well. By the end of the day, you will be in a position to draw the structure of ozone. And then when you draw the structure of ozone, you will see one of the oxygen is positively charged. The other, one of the 3 oxygen is positively charged. And then one of the oxygen is negatively charged. +1, -1, 0, giving us a neutral ozone molecule, okay? So.
Okay.
Okay.
Understood.
So we have, in this particular molecule, we have 2 oxygens. One of the oxygen is negatively charged. The other oxygen is neutral, okay? So we do not have any issues with this part, okay? With this part, we do not have any issue. With this part, we do not have any issue. In both cases, they are the same, okay? The issue we have is, in one case, in this particular case, in one case, the carbon-oxygen double bond is this carbon oxygen bond is a double bond. In the other form, this carbon-oxygen bond is a single bond. In this form, this carbon-oxygen bond is a single bond. In this other one is this carbon-oxygen bond is a double bond. In this particular example, this oxygen A is neutral, while in this other resonance form, that oxygen A is negatively charged. In this one, in B, oxygen in structure number 1, oxygen B is negatively charged, while in structure 2, oxygen B is neutral. But all the same, you see 2 types of we observe, okay, let me just put it, we observe 1, 2 types of carbon-oxygen bond. Isn't it true? We have a carbon-oxygen double bond. Then we have carbon-oxygen single bond. Okay, carbon-oxygen double bond. And then a carbon-oxygen single bond. In the acetate ion, we can observe 2 types of carbon-oxygen bonds, a double bond and single bond. Remember, double bonds are shorter, isn't it? This will be short. The other one will be long. That's one of the things we observe. The other thing we observe, we have 2 types of oxygens. One of them neutral, the other one is negatively charged. This is what we see, okay? And then we are noting what we are observing. Two types of oxygen, neutral oxygen and negatively charged oxygen. So, is it very clear? Hello? Hello?
Yes.
Very
Yes.
clear, isn't it? Very clear.
Yeah.
We see two types of we see two types of carbon-oxygen bonds, and then we see two types of oxygens. One of the carbon-oxygen bond being double bond and short, the other bond being a carbon-oxygen single bond, therefore long. One of the oxygen being neutral,
Yeah.
the other oxygen being negatively charged, isn't it?
Yes.
Okay. Now,
Yes.
this is our observation. Also, please mute. Please mute. This is our observation. How about experimental fact? What is the experimental fact? See, our observation tell us in the acetylene, we have two types of carbon-oxygen bonds. One of them should be short, the other one should be long. That is one. Our observation says one of the oxygen is neutral, the other one is negatively charged. But what is the experimental fact? What is the result when you conduct an experiment to measure the carbon-oxygen bonds? Experimental fact tells us both carbon-oxygen bonds have the same length and strength. They are the same in terms of their length and also in terms of their strength, which is contrary to what the Lewis structure is telling us. That's one observation, one experimental fact about this molecule. The second one, the charges on both oxygens are the same. And both are negatively charged. Now, from here, there's a contradiction, isn't it? Between the theory and the experimental finding. The theory is telling us we should have two different types of carbon-oxygen bonds. The theory also tells us the charge on the two oxygens should be different. One of them should be neutral, the other one should be negatively charged. But experimentally, it has been found that both carbon-oxygen bonds are one and the same in terms of their length and strength. Experimentally, it's also been found the charge on both oxygens are the same. Then both of them have negative charge. So what this is telling us, I want you to know that the structure of the acetylene is neither 1 nor 2. If the structure of the acetylene is either 1 or 2, the experimental finding should tell us one of them is long, the other one is short, etc. But it has been found that the bonds, the carbon-oxygen bonds, are one and the same. The charge on the two oxygen atoms is the same. So the only way that is possible is if the structure of the acetylene is neither 1 nor 2, but the average of the two. Okay? The composite of the two. So the structure of the acid ion is neither 1 nor 2, but the composite of the two, the average of the two, the weighted average of the two. Is it okay? Hello? So one of the things I want you to understand first, yes. One of the things I want you to understand first and agree with me that if the structure of the acid ion is either 1 or 2, if it is either of them, the experimental facts should tell us one of the carbon oxygen bond is a double bond, short and strong. The other carbon oxygen bond is long and weak, etc. And one of the oxygen is neutral, the other one is negatively charged. But experimentally, it has been found that the length of this carbon oxygen bond, you see this carbon oxygen double bond, you see this carbon oxygen single bond, the length of this carbon oxygen bonds, you see this carbon oxygen bond and this carbon oxygen bond are the same. It is also telling us, the experiment is telling us, the charges on both oxygens are the same, and both of them have some negative charge. So what this is telling us, the structure of the acid ion is neither 1 nor 2, but the average, the composite, the weighted average of the two structures. So you take 1 and 2, you mix them together, you get an average, and that average will be the structure of the acetate ion. Is it okay? So let me now, with this background, let me take you back to my slides, okay? Are you guys okay with this? Hello?
Yes. Yes, we are okay.
Okay. Now let me unshare this and share my slides, okay? So that we can have further discussion based on our lecture notes. So we were talking about resonance, okay? So by definition, what resonance means? The property of having a structure, a molecular structure, which cannot adequately be represented by a single structure, but is a composite of 2 or more structures, okay? The property, resonance, is the property of having a structure that cannot adequately be represented by a single structure. The way we have seen for the acid ion, we cannot represent it by a single structure adequately. We have 2 structures, at least, and then the true structure is a composite of the 2, or the more of the 2 structures in the case of the acid ion. We'll see later, there are some structures that can be represented by more than 3, 4, 5 structures, okay? Then you take the average, that will be a structure of the molecule. And then each of these different structures have high energy or are unstable. I will talk about this part, the stability, the energy part later. So let me go back to resonance, okay? Some compounds cannot be adequately represented by a single Lewis structure. As an example, let's look at the acid ion CH3CO2 minus, this one. When you draw the Lewis structure of this structure will suggest to us that in this molecule, we have 2 types of carbon-oxygen bonds. One of them being a double bond, the other one being a single bond. The Lewis structure of the acid ion suggests that the 2 carbon-oxygen bonds are different. One of them being single bond and negatively charged, the other one being a double bond and neutral. That's what this structure suggesting to us. But experimental evidence, however, indicates that 2 carbon-oxygen bonds in the acid ions are equivalent in terms of their length, in terms of their strength. And the charges on the two oxygens are the same. So the charge on this oxygen as well as the charge on that oxygen are the same. In fact, experimentally, it has been determined that both carbon-oxygen bond in the acid ion have a length of 127 picometer. They are 127 picometer in length, 127 times 10 to the power of minus 12 in terms of the length. This bond length of 127 is intermediate or midway between the carbon-oxygen single bond and the carbon-oxygen double bond. You remember single bonds are longer. So the carbon-oxygen single bond is about 135 picometer. But the carbon-oxygen double bond, since it is shorter, it's about 120. But when the carbon-oxygen bond in acetate ion was determined, it was found to be 127. Intermediate between thereof a single bond and a double bond. So the carbon-oxygen bond in the acetate ion in terms of strength and length is somewhere in between a single bond and a double bond. It's neither a single bond nor a double bond, but an average of a single bond and a double bond. Okay? Then each of the oxygens, when their charge was determined, it was found to be negative. From the Lewis structure, we see one of them is negative, the other one is neutral. But experimentally, what is found that each of them is negatively charged. So you see, remember in the structures I've shown you, in structure 1, oxygen B was negatively charged. In structure 2, it was oxygen A that was negatively charged. So if you take the average, if you add the two and divide them by 2, you will see that on each of the oxygen will have some negative charge. In terms of the length, each of the carbon-oxygen bonds, they will be intermediate between a single bond and a double bond. Because the carbon-oxygen bond in resonance in form 1, it is a double bond. The same in form 2 is a single bond. So on the average, it is an intermediate between a double bond and a single bond. It's neither a double bond nor a single bond. So the Lewis structure we drew does not depict this reality. The reality that the two carbon-oxygen bonds are different from it, are identical with each other. The Lewis structure is telling us the two are different. So the experimental observation for the acid anion are better represented by a picture in which the electrons are equally distributed between the two oxygen atoms. So for the acid ion, we can draw two structures, maybe drawn for the acid ion, each having the same connectivity, but the only difference being in the location of the pair of electrons. You remember when drawing the Lewis structure of the acid ion, we followed the steps. The first step was to determine the arrangement of the atoms, how the atoms are connected to each other, which one is next to each other. So these two structures have the same connectivity, but the only difference between them is in the location of a pair of electrons, the pair of electrons. In the case of this form, this oxygen has got 2 lone pair of electrons. The lower oxygen has got 3 lone pair of electrons. In the other resonant form, the lower oxygen has got only 2 lone pair of electrons, but it is the upper electron that has got 3 lone pair of electrons. So this additional electron, 1 pair of electron, in one case, it is in the lower oxygen. In the other case, it is in the upper oxygen. So these structures differ only in the location of the pair of electrons. The two structures may be drawn for the acetate ion, each having the same connectivity, differing only in the location of the pair of electrons. So we draw these two structures, and these two structures are related as structures of the same molecule. They are the average of these two molecules, and the relationship between them is represented by a double-headed arrow, as we shall discuss in a short while. So now, to reconcile this observation, theoretical observation, as seen by the Lewis structure and the experimental observation, a theory is developed. This theory is called resonance. Resonance is a theory developed to reconcile experimental data with implications of Lewis structures for compounds with two or more structures. So that compounds that have two or more structures cannot their property cannot be adequately represented by any of these single structures. As a result, there is a theory that's developed. This theory is called resonance. Okay, now I don't want you to be confused and lose focus. We came into resonance because we failed to represent the structure of the acetate ion by a single structure. If you represent, following the steps in drawing Lewis structures, if you are able to represent the structure of a molecule by a single structure, that is the theory, and the experiment will be consistent. We don't need a new theory. The Lewis theory is enough to describe that. But if you have a situation where we fail to adequately represent the structure of a molecule by a single structure, now the Lewis theory is not going to apply. Is not going to explain what is observed experimentally. So to reconcile the Lewis theory with experimental facts, a new theory is developed. And then this new theory is called resonance. Then by definition, resonance, as I've told you, is the property of having a molecular structure which cannot adequately be represented by a single structure, but a composite, an average of two or more structures. And then, as you shall see, each of these structures have higher energy than the average or the composite. We'll talk about that later. Okay, so the individual structures are the ones that contribute towards the structure of the molecule. Remember, for the acetate ion, we drew two different structures, structure A and structure B. These are the individual structures. Then these individual structures contribute towards the resonance structure of the molecule, towards the actual structure of the molecule. The individual structures are resonance contributor to the structure of the acetate ion. And then it is pictured as a resonance hybrid of these two structures. Okay? So the true structure of the acetate ion is a resonance hybrid of the two structures. Then these two structures, the only difference between the two structures is in the arrangement of electrons. Otherwise, the way the atoms are connected to each other is the same as determined by step 1 of drawing Lewis structure. There is no difference in the position of the atoms. It's the same. The only difference between the structure is, like in this particular case, where should the additional one lone pair of electron be? Should it be on the oxygen, the upper electron oxygen, or the lower oxygen? That's the only difference. Then as a result of that, we have one case where the additional one pair is in the lower oxygen. In the other case, where we have the additional oxygen, electron is in the upper oxygen. So the actual properties of the acid ion cannot be adequately represented by any of the Lewis structure taken alone. If you look at each of the Lewis structure of the acid ion individually, you will see you have a single bond, a carbon-oxygen single bond, and a carbon-oxygen double bond, totally different types of carbon-oxygen. So as a result, the actual property of the acid ion cannot be adequately represented by any of the Lewis structure taken alone. The experimental facts are represented by drawing the two resonance contributors. So now let's look at the acid ion. Okay, so let me stop sharing this one, and then I go back to the note, to what I was drawing, and I share with you, okay? Now, let's draw the true structure of the acid ion. So the true or the actual structure of the acetate ion is a resonance hybrid composite or average of the two structures, okay? Of the two individual structures. So what we know and we are certain about, we do not have a problem with the first carbon. On the first carbon, we have the 3 hydrogens, okay? Here we do not have a problem at all. And then we know this carbon is attached to another carbon. Then this carbon is bonded to 2 oxygens, one here, another here. But what we observed in one of, what we observed in one case, we have a carbon-oxygen double bond here. In the other case, we have a carbon-oxygen single. In one case, we have a carbon-oxygen double bond here. In the other case, we have a carbon-oxygen double bond here. So each of these carbon-oxygen double bonds can be double bonds. Of course, you cannot have a double bond here and a double bond here. That's not possible, because that carbon will have 10 electrons. It will have more than the number of electrons in the first place we had in this molecule. So we can have a double bond here. We can also have a double bond in here. So that each of the carbon-oxygen double bonds have some kind of double bond character. Each of the carbon-oxygen double bonds are intermediate between a single bond and a double bond. You remember what the experimental data was telling us, that the carbon-oxygen, the length of the carbon-oxygen bond, if it is a single bond, it is 135 picometer. The double bond is 120. But for the acetate, this bond, the length of this bond was 127. Each of them, 127, 127. What is this telling us? The carbon-oxygen bond in the acetate ion is neither a single bond nor a double bond, but an intermediate between a single bond and a double bond. So in terms of double bond, in terms of bond order, if you look at the bond order is 3/2 or 1.5. The bond order for a single bond, it is 1. The bond order for a double bond is 2. The bond order in this particular molecule is 1.5, intermediate between a double bond and a single bond. What we have also observed that in one of the resonant form, this oxygen was negatively charged. In the other resonant form, it was the other oxygen that was negatively charged. So the negative charge is shared equally between the two oxygen atoms. You remember the acetate ion has a -1 charge, -1. This -1 charge is shared equally between the two oxygen. As a result, the charge on this oxygen is -½ while the charge on this oxygen is -½ plus -½ is equal to -1. The -1 charge is shared equally between the two oxygen. That's why the experiment is telling us that both oxygens have the same charge. Both of them are negatively charged. It is intermediate, half of -1. So each of them have -½ charge. Then each of the bonds of the carbon-oxygen bond are intermediate between a double bond and a single bond. To show a bond that is intermediate, we use dashed line, because if you put a solid line represents a full bond, okay? I cannot put a full line in here or a full line here. If I put full lines, it will be like you have a double bond in here and then another double bond here, which is not the case. So this bond is neither a single bond nor a double bond, intermediate between the two, an average between a double bond and a single bond. Each of the carbon-oxygen bond have some kind of double bond character. To show that, we use this dashed line. So this is the Lewis, This is the structure of the acetate ion. Okay, the acetate ion is neither 1 or 2. It is the average of the two. It is the composite of the two structures. It is the weighted average of the two structures, and it is this one. Okay? Is it clear? Hello?
Yes. Yes.
Okay. So let me just go back to my notes, our slides, and finish some things before. So the resonance structure, so this is basically the structure of the acetate ion. Okay? So -½ here, -½ here, and then each of these bonds are intermediate between a single bond and a double bond. As you can see, on both oxygens, we have 2 lone pair of electrons. In one case, the lone pair of electrons is on this one and the other one. That's why we do not put that. We represent by this -½ -½ okay, like that. So the resonance relationship among different resonance structure is represented by a double-headed arrow. This double-headed arrow you put between resonance structure to indicate, to indicate that this one and these ones are resonance structures of each other. Then that both of them contribute towards the structure of the molecule. Okay. So the double-headed arrow means that the molecule is an average of all contributing structures. The molecule is said to be a resonance hybrid of these structures. The symbol does not mean that the two forms are in equilibrium with each other. This does not mean the two forms are in equilibrium with each other. We are not implying a chemical reaction, except that to show that these are contributors towards the reaction. Okay. So there is only one structure for the acid ion, which is a hybrid of the two structures drawn. And then the only difference between the resonant form is the placement of the pi and the non-bonding valence electron, which I will elaborate from our next lecture. Okay. Now, do you have any question on what I have discussed so far? And it's very important you understand the concept of resonance. Do you have any question? Okay, so what I want you to do, you take your time and try to understand this concept and understand it very well. Then I will, in our next lecture, I will start by revising this and then add additional concepts related to energy. Remember what I told you? That resonance, the different resonant forms have higher energy than the structure of the molecule. For example, in the case of the acid ion, we have resonance contributor 1 and resonance contributor 2. And then we have the actual structure of the acid ion. Resonance contributor 1 and 2, both of them have higher energy than the structure of the acid ion. And then we'll see why this is the case. Okay? So see you on Wednesday. Bye-bye. Unless you have a question.
Yes. Excuse me, sir.